So would you hate it so much if I make the due date of the project on Monday, the 11th? December 8th. Yeah, I thought so. So yeah, if you're done with it, turn it in. If you need the extra couple of days, especially Wednesday group, they will have their lab report due on Friday. So, couple extra days for your project. Huh? Isn't that Monday? So if Friday, yeah, yes. So that would be, but if you want it earlier, that's fine, Billy. I thought you were just like, don't crash, yeah. Okay, and today, everybody in the room will get plus 10. That's your attendance.
Sarah feels really sick though today.
She didn't send me a note. And I didn't know she was not here, so I didn't make it on purpose. Okay, I'm not going to take it back, so, yep.
Is this in addition to the possible plus 20?
Yeah, that's the plus 20 is for anything that you do, like you turn in homework and stuff like that.
Plus 10 is on top of that.
On top of that.
Cool.
Yeah, that's what the syllabus says. Okay, good. Thank you for being here. You've been awesome in the lab too, so it's great. Okay, let's all right. Let's try to remember where we were last time, especially that all of you had lab as well, so this should be ingrained already. So what is saponification value used for? Lynn. It's a way to measure the molecular weight of triglyceride and specifically the average molecular weight of the fatty acid in your triglycerides. And it's also unique for every oil. So it's kind of an identification method. Okay. What test is used when testing? That's very odd. Efficiency of hydrogenation. Okay, Lucy? The iodine value. So because it's a measure of unsaturation, so when we hydrogenate, we saturate the oil. So we test it before and after to determine the efficiency of the process. What could happen during hydrogenation as well if it was incomplete? What you could form? Trans, yes. So if it was an incomplete hydrogenation, trans fatty acid could be formed. Okay. So presence of free fatty acids is an indication of what, Katie? The age of the oil and the level of refinement. So the age of the oil, what could happen during aging? Yeah, okay. Justin, you have your hand up since before. Hydrolytic rancidity during aging, if you have lipases in there. Were you going to say something different? The oxidation won't impact the free fatty acid. Presence of free fatty acid will impact oxidation because they're more prone for oxidation. Another thing we talked about has to do with, Monica? Frying oil. So when you have water from your food and heat and the oil, so the water and heat will induce hydrolysis of the triglycerides and release fatty acid, and the more you fry with the same oil, the higher the amount of free fatty acid that will get oxidized, and you'll get nasty flavors as well as bad for your health. Okay, if oil A has higher saponification value than B, which one has lower average molecular weight for fatty acid? We did that exercise last time, Walter? Yes, so it's an opposite. Somebody said very simply, in the denominator, you will have the higher value. That was the simple way of thinking about it. The more complicated way is 1 mole will weigh less than 1 mole of a smaller molecular weight. fatty acid. Name few physical characterization tests linked to burning the house down story. Okay. Smoke points. You were going to say something, Molly? List them all. The fire hazard, Tehu. Cold test. What would we measure it for? Winterization, effective winterization process. Refractive index, which is used for identification, is correlated with the saturation of the oil. Justin? Consistency and spreadability is another term, another physical measurement. Okay, cool. Moving on. So, free fatty acid test, which you already did in the lab, and we talked about when we need to test it. And it's simple, same as titratable acidity. You basically titrate with a base to a pink endpoint in the presence of phenolphthalein indicator. The thing we talked about in the lab is you always use the molecular weight of oleic acid, which is not necessarily the dominant fatty acid in all the oils. But you would get it in terms of the oleic acid, and then you correct it by using a factor. For every type of oil, the dominant fatty acid will be used in terms of a factor, conversion factor. So palmitic, for example, you will multiply by a factor of 2.19. Okay. Okay. Moving on to measuring oxidation. So you study in food chemistry the oxidation of fats. Here we measure the oxidation of fat. So there is the current state of oxidation. That means now, what does the oil look like now in terms of oxidation? So the first one is peroxide value, which is the primary oxidation product. Peroxides are the primary oxidation product. So you would measure them, and the peroxide value is defined as milliequivalent. Again, this is important. Milliequivalent of peroxides per 1 kilogram of sample. So a freshly refined oil or fat will have a peroxide value of 0. What about a very oxidized oil? 0. Okay, because it's a primary oxidation product, then it will move on to secondary, and the peroxides will decline over time. So you will have something that you will plot, hopefully for at least one of the oils followed this trend. Okay, I can erase this now. So you will have a bell shape. Okay. So this would be time, and this would be peroxide, and milliequivalent per 1 kilogram of oil. And then hopefully you're starting with a fresh oil. So when it goes up, peaks, and even when it's going up, the secondary oxidation is still happening. But then it will peak, and then the secondary oxidation is faster than any more peroxides formed until a really oxidized oil. So 0 does not always mean fresh oil. How can we tell them apart? Two oils, both peroxide value of 0. How can I tell them apart? Katie? You could, but there's an easier way. Just smell them. One is going to smell really bad. So yes. All right. So how you did it in the lab, you reacted your peroxide, if they were present, you react them with potassium iodide, and then you generate iodine. The iodine, you add the starch, you get that dark blue or purplish color, and then you titrate with sodium thiosulfate. The concentration of sodium thiosulfate depends on how much peroxides you expect in your oils. That's why we changed it in the lab from 0.1 to 0.002 because we were not expecting to have a lot. And if we start with the really concentrated sodium thiosulfate, we will not see the endpoint. One drop will be done and you get a pink. So we dilute it so that we have enough volume to measure, knowing that we are starting at least with fresh oils. Okay, and then we titrate to colorless, and since it's milli-equivalent, so you'll notice the equation doesn't have a division by 1,000 because it is milli-equivalent, so you don't have to convert milliliter to liter by using the or dividing by 1,000. And now here you see we multiply by 1,000 because you divide in weight in grams, so it will be per 1 gram, but you want it per 1,000 grams or per 1 kilogram, so you multiply by 1,000. So that's that, and that's what you did in the lab. Another more accurate, I would say, a measure of oxidation is the anisidine and the TOTOX value. In this case, you don't only look at primary oxidation product, you also look at secondary oxidation products such as aldehydes. So here the reagent will react with unsaturated aldehydes and gives you a chromogen that will be measured at 350. So then you'll get the anisidine value, and the TOTOX value, which is even better, you will take into account the anisidine value and also the peroxide value. And this is an example of a fresh oil in terms of anisidine alone and TOTOX value, which combines both anisidine and peroxide. Another measurement that is really for secondary oxidation products is to measure the volatile organic compounds. Mostly hexanal was used. You can measure pentanal as well, but hexanal, if it's present, that means you've reached secondary oxidation stage. So it's very easy because you don't we need to see if they have lipid oxidation within a complex food matrix, you don't have to extract the oil out. You can just have a headspace method for GC, and the volatiles will be detected using GC FID. So it is really easy to run if you know how to work with GC FID. And just measure the presence of hexanal, which is correlated with oxidation, and it also is correlated with sensory evaluation, given that off flavors can be detected. Now, TBars, which is thiobarbituric acid reactive substances, so this test you will do in chemical reactions. I did update the slides a little bit. So thiobarbituric acid reactive substance is the complete name of the test, and it's commonly known as TBars. So you'll run this test in chemical reactions, and it does measure secondary oxidation products, specifically malonaldehyde. And malonaldehyde is a direct derivative of the oxidation of linolenic acid specifically. So what happens if you have this secondary oxidized product or secondary oxidation product that will react with TBA, which is thiobarbituric acid, to give a colored compound. Again, it's a spectrophotometric method. You measure it. And it also correlates with sensory evaluation because peroxides, if they're present, that doesn't necessarily you can smell anything. They're not volatile. You cannot tell if there has been any oxidation. But definitely secondary oxidation product can be detected by sensory evaluation. There are disadvantages. Malonaldehyde can react with other compounds, not necessarily TBA, so it might go undetected, and therefore it might not be too much sensitive if you don't have a lot generated, especially if your oil doesn't have that much linolenic acid, so the assay won't be sensitive and it won't be an indication if you have secondary oxidation products or not. Alternative method to a spectrophotometric method, if you really want to measure minute amount of this, it would be HPLC. And there is a common method that can be used to measure the different aldehydes that can be generated. Okay? So one of the most used application is to measure lipid oxidation in meat products. Okay. Evaluation of the oxidative stability, which you kind of did in the lab. You did a little bit of that. It wasn't an extended period of time, but you did accelerated kind of shelf life storage or accelerated oxidation storage study. So, and what you did is really an oven storage test, but the temperature was really high and we did it over 24 hours. But the regular test is you do at 60 degrees and you actually save your samples or store your sample for longer period of time, not 24 hours, so that you can see impact. And why would you want to store to determine oxidative stability? This is usually used to determine something we call induction period. That means the period before the oxidation starts. So kind of like your shelf life really before the onset of oxidation. This is sometimes helpful for test if you want to test natural antioxidants versus synthetic antioxidants to see how they compare to synthetic antioxidants. So you will have your oil with no antioxidants, an oil with synthetic, and an oil with natural. Or not necessarily an oil, but let's say carotenoid or anything else. If you need to use your phone, this is the third time, maybe fourth time this semester, please step outside. Okay. So there are different ways of testing the induction period. One is the oven storage test, which is basically what we did in the lab, but like I said, at lower temperature and extended period of time. So usually it's a 60 degrees Celsius, and you put your oil samples, and then you take out an oil sample every certain increment of time or interval. And then here you measure either peroxide value or TBars or hexanol. Usually it's peroxide value is what measured, because you just want to determine the onset of the initial oxidation state. Okay, so that's simple. The other one that can be used, and usually there is equipment for it called Rancimat. You might come across that either when you're looking in your project. You might have seen this. But oil stability index is basically you get your oil and you put it in a temperature around 110, 130 degrees Celsius, and then you boil in or bubble in oxygen. So you bubble in oxygen or air even, and then volatiles will start to evaporate or leave the system, leave the oil, mostly formic acid, and this volatile will be captured in a tube system, and then it will go into water container, and then conductivity will be measured. So as formic acid starts to form, the conductivity will change, and then you can determine the onset of oxidation that way. The oxygen bomb, it can be used, actually it can be used with intact food. It doesn't have to be an extracted oil. What you would do is you put your sample, whether it's a food sample or oil sample, you put it in a chamber and you pressurize this chamber with oxygen. And there will be a pressure gauge that you can read the pressure. And then once the oxidation starts, there will be a drop in the pressure due to pickup of the oxygen. And that would be your induction period. And actually the chamber, I forgot to mention, you would put the whole containment in boiling water. basically. You want to have some heat. Okay. Yeah. Well, heat will accelerate oxidation. So it's accelerated shelf life studies. So you accelerate it and predict shelf life without heat. Yeah. Okay. So fat characterization include also looking at the different lipid fractions. So we will look at fatty acids, the composition of fatty acids, mono, di, and triglycerides. Mono and di are important to measure because mono and di, they don't contribute to 9 calories. So you want to make sure you factor that in. And then phospholipids, cholesterol, lipid-soluble pigments, and vitamins. So they're all under the lipid fraction, but they are actually different components of the lipid. So for labeling, we really need to quantify saturated, mono, polyunsaturated, trans fat for nutrition labeling. So that's important as well. Yeah. They do not contribute to exactly 9 calories because they mono and di. You don't have the triglycerides in there. Same as with short chain and medium chain fatty acids as well. Okay. So for fatty acid analysis and determining of let's say the total calories from fat, you do the saponification, right, usually, and you do the methylation and then GC. Do you remember what olestra is? Huh? Yes, Lauren? Yes. So it's basically fatty acids and sucrose, linked to sucrose. So yeah, it is not absorbed. It doesn't contribute to calories. So if you have, but it is a non-soluble component. So it will be fractionated with your oil. So if you want to differentiate how much olestra you have versus actual fat, so it's not saponifiable. Or it's actually saponifiable. You will if you saponify, you'll break off the fatty acid of the sucrose and you'll quantify it as fatty acid that contributes to calories. So you don't want to do that when you suspect you have olestra in a food product. So what you would do really in this case is you hydrolyze your triglycerides by lipase. So instead of saponification, you use enzyme. So the lipase is specific for triglycerides, so it will not break off fatty acids from the sugar. Okay? So you hydrolyze by lipase, precipitate with calcium hydroxide. You can precipitate the fatty acids and separate them from olestra. And then you go through the methylation process and do GC, like we did. So the characterization of these fractions can be done by GC methods. If we do mono and di, sometimes you use LC with nonpolar phases or columns. And of course, if you link to MS, you get better identification. So if you do thin layer chromatography, and I'll show you an example in a minute, you can do qualitative determination of the different components you have in your sample. So the GC methods, you did that already, the fatty acid profiling with fatty acid methyl esters. We use it to determine composition and adulteration. And then if we want cholesterol, that's one of your questions, I believe, in one of the lab reports. So what is a non-saponifiable matter? Cholesterol is not saponifiable. So what you do to determine cholesterol is you get your fat or lipid fraction, you saponify, you get fatty acids that are soluble, water soluble, right? So before methylation, that is. So they're still water soluble, You have your fatty acid. The cholesterol is non-saponifiable. It will remain soluble in the organic phase. You will separate the aqueous from the organic, take out the fatty acid, that is, we don't want them, and then the cholesterol in the organic solvent will then be derivatized to trimethylsilyl, which are volatile and thermally stable and can be detected by GC. So here's an example of thin layer chromatography. So it's rapid analysis to determine the presence of different fractions. So you use silica, basically silica gel that is impregnated with water. So your stationary phase is polar. And you resolve with a nonpolar solvent. So look what happens. So the first, you put standards and then your sample, and then to identify what's in your sample. So this PL is for phospholipid. It's a very polar lipid. So look at here. It stays interacting with the silica gel. It won't move with your mobile phase. It will interact the most and stay put almost. And this is mono acetylglycerol and diacetylglycerol. That means mono glyceride and diglyceride, basically another term for that. So again, the mono is more polar than the di, and then more polar than the free fatty acids. And this would be your triglyceride, the most nonpolar component that travels the most. And here are two set of samples, and you can see what you have in your sample based on your standards. Already done the lab. Any questions on fat characterization? Okay, next. So the next best thing in the world is protein separation and characterization. Okay, is it the next best thing, Claire, or the best thing? What? You're questioning this? It's the best thing. That was the correct answer. Or is it fiber for you now? Okay. All right, so moving on from fat characterization to protein characterization, but before we characterize a protein, it has to be isolated and separated. So that's why we talk about protein separation and characterization. And it's not, protein separation can be more complex than fat separation. Where fat, you put organic solvent and get the fat out. It's not as easy with proteins. Okay. Sam. Okay. Why do you want to say all of the above? Seemed correct, yeah? No, it's all of the above. It is all of the above. So different proteins will have different solubility in different pHs and different salt concentrations. So you can use the solubility in organic solvent. They are not soluble. So you use the differences in solubility of protein versus carbohydrate versus lipid, or proteins. If you want to purify one type of protein, then you can change the pH, salt, and isolate one protein from a mixture. Adsorptivity is important because sometimes you use chromatography and different types of chromatography, so different proteins will adsorb differently with stationary phases. So it is used typically for protein separation. Denaturation, yes, you can heat up the solution and then precipitate the protein. They aggregate, precipitate, and you can pull them out of solution. B? Sam? You were going to say B, Sam?
I was going to say all A, B, and C.
Yes? It's actually all of the above. So you can use size exclusion to separate them based on size. You can salt them out by changing the concentration of salt. Electrophoresis is typically used to separate proteins based on either size or size to charge ratio. Why do we care? Why do we want to separate protein? Why do we care about separating proteins? Anything? Carmen. So you wanted to separate it to test its functionality? Sure. Yeah. Yeah, so characterization of the protein. So you isolate the protein. Let's say I can take whey protein out of milk. I can take casein protein out of milk, and then look at the different solubility of these two proteins and how they behave under different conditions. Yes. What is very important application that you didn't mention? Think industry. What? So before we make the foods, we make the isolates, right? We prepare protein isolates to be used as ingredients. So in food or food ingredient production. So we isolate protein to use them as ingredients. We purify protein, like you said, for further analysis, identification, characterization of functionality, the chemistry of it, understanding how it differs from one protein to the other, or to purify a protein as an enzyme to use it in an assay, or to purify casein to use it for a trypsin enzyme activity test, for example, or a chymosin, or the rennet. If you want to do rennet activity, then you need a casein substrate to test rennet activity. So a little bit back to some food chemistry knowledge. Proteins differ in so many different things. Nutritional quality, which has to do with the amino acid composition and digestibility. Functional properties, some will gel better than others. Some proteins are more soluble. Some will emulsify. Some will foam better. But the most important thing that we rely on for separation is the biochemical differences between the different proteins. And that's the characteristic that we rely on to design our separation. So biochemical differences, what does that mean? So the solubility and thermal stability. So the solubility is impacted by their size and their charge, and basically their amino acid composition. So a protein that is high in hydrophobic residues will have poor solubility. A protein that is high in hydrophilic and charged amino acid will have high solubility. Thermal stability, let's say a protein will denature at 70 degrees versus a protein that will denature at 140 degrees. So we can separate them by enforcing the denaturation of one of the protein. By reaching that temperature, we'll aggregate, precipitate, and we can separate it. So size, we can use size exclusion or membrane filtration to separate the protein based on their size. Charge, that's where pH and salt can be used to separate proteins based on their charge. You can put certain concentration of salt and one protein will precipitate while another won't if it has higher net charge than the first protein. So, and also you can use charge to do ion exchange. You can separate them using cation and anion exchange. Adsorptive characteristics, such as we'll see that in hydrophobic interaction chromatography, which is very much used to separate proteins, and also affinity chromatography it relies on the adsorption characteristic of the protein to the stationary phase. Biological affinities, which has to do really with affinity chromatography, if you use antibodies, for example, to separate the proteins, or enzyme inhibitors if you're separating enzymes, for example. So salting out. So how it works is that you have a protein with a certain net charge, then you will add, let's say, ammonium sulfate. The ammonium sulfate is going to, the sulfate groups, if it's positively charged protein, is going to start shielding the charges and preventing the protein from interacting with water. And also the presence of salt will compete for water, compete for interacting with water. So at high concentration of salt, the solubility of a protein will be decreased. Okay? So let's say you have this mixture, A, B, C, D, and E. And then you increase, and you have higher charge E at a particular pH, let's say neutral pH. At pH 7, the highest net charge, E has the highest net charge. How do we separate C from the mixture? Okay.
Would you first separate A and B, or D and E and A?
How do you do that? I mean, good. You're heading in the right direction, Mallory.
Maybe figure out how much salt you need to precipitate or to salt out two of them, and then do the other two.
Yes, that's exactly what it is. Of course, it's not as simple as this. You should know all the proteins, and you should know all the charges, and you will start with different concentrations of salt to know that you would know that A and B will precipitate, while C, D, and E will stay in solution. Because these has lower charges, so they will separate at lower, or precipitate at lower concentration of salt. So A and B will separate or precipitate, and then you'll have C, D, and E in solution. So you take the supernatant, then you increase the salt a little bit more, precipitate C, collect that, D and E will remain in solution. But that's a very simple, this simplistic example, but just to have you understand it a little bit. You can precipitate protein and isolate it. Let's say you have milk. Milk precipitate at 4.6, which is the isoelectric point. That means casein doesn't carry charge when the pH is 4.6. So that's how yogurt is formed, right? You have lactic acid generated during fermentation until you reach a pH 4.6, and then the casein precipitate because of net charge. And here's just a reminder how you would normally get the isoelectric point, but it is really the pKa1 and pKa2 divided by 2. But yeah. Solvent fractionation. So proteins are usually insoluble in alcohol. So protein will be reacting or will be interacting with water. Once you have acetone, the acetone replaces water on the surface, so the protein no longer interacting with water, and it will precipitate. Or you can denature the protein and let it coagulate or polymerize. So basically the protein will open up, hydrophobic groups will be exposed, they will not like water, so they will interact with each other. If you have disulfide bonds, it will form covalent linkages, and you will have polymerization that is irreversible, and then forming big aggregates that will precipitate, fall out of solution, you collect them, and that's that. So here's the example of casein. If you have a mixture of casein and whey protein, you can actually heat to higher than 73, collect the whey protein while casein still is stable at that temperature. Here's an actual example of how you would separate a protein, starting with your raw ingredient or raw product, which is in this case defatted soy flakes. So the soy, you flake the soy, press the soy for oil, and then you end up with flakes that are defatted. So they're rich in protein and in fiber. So you want to separate the fiber from the protein, from oligosaccharides, from the sugars that could be in there as well. So there are two ways you can do that. One way, which is a very common way to get the purified protein extract, you solubilize the protein in alkaline pH, usually 7.5 to 8. The protein will solubilize, your fiber will precipitate. Fiber will not be soluble. So you would do acidification. That means whatever present with or soluble with the protein, you have small sugars, you might have some hydrocolloids that are water soluble, some oligosaccharides that could be soluble with the protein. You want to isolate that even further. You will bring down the pH to the isoelectric point of the protein. So now the protein will precipitate. Everything else that is soluble in water will remain. So you purified that even further. You do few wash to remove any residues, neutralize, because you don't want to leave the protein at the isoelectric point. It will be non-functional. And then you spray dry, and then you get an isolate of 90% protein or higher. Another way is you use alcohol, aqueous alcohol. What will get solubilized in aqueous alcohol? Do you remember from your total carbohydrate, from the carbohydrate lecture? Nobody knows what's soluble at that? I'm sure many of you knows, other than not only Monica knows. Aqueous alcohol with heat. Huh? Yeah? Go ahead. Yeah, but what will be soluble in alcohol? Yeah, what, Emily? Huh? What? Yeah. But what saccharides? Yeah, disaccharides, oligosaccharides, monosaccharides, small sugars will be soluble in 80% alcohol, aqueous alcohol. Then what will precipitate is your protein and fiber will precipitate. Then you will have a concentrate that is high in fiber but low in sugars. Okay? And it is high in protein as well, because the flake is about 50% protein. So you take out some of the sugars, and then you'll end up with even more concentrated protein product, which is used for extrusion and texturized soy protein product. But anyway, so you can either get a more purified protein or a very purified protein, depending on what steps or solubility you rely on. Separation by adsorption. So here's where chromatography is utilized. One of the common chromatography used for separating protein is ion exchange. Why is that? Simply. Sam? Because proteins are charged molecules. So we can use anion or cation. Why are we able to use two? Anion and cation for the same protein. There are both positive and negative, but the protein either has a net negative charge or a net positive charge. That's the key. Based on the pH of the solution. So based on the pH of the solution, you can force your protein to either have a negative charge or a positive charge. So depending on the column you have and the capabilities and the net charge of the protein, you might select one or the other depending on what is easier to do. So basically your protein, let's say it's negatively charged, it's anion exchange, and the higher your net charge, the more interaction you have with the column. And once the protein is interacting with the column, the way we help it elute, if you remember, is you change the ionic strength. We change the salt concentration so that the salt competes for binding sites with the column or the stationary phase, and the protein will elute. pH, also you can change the pH by increasing the pH, for example, and then you will start losing the positive charges on your stationary phase because they will start donating protons to your buffer. Then the proteins will no longer interact with the column. So often, because proteins are large molecules, so you use polysaccharide-based resins because then you will have bigger pores for the proteins to interact with the stationary phase. I have a note here, pI of a protein is important. If we know the pI of a protein, we can determine the charge at a particular pH. So if the pH is higher than the pI of a protein, what would its net charge be? If the pH of your solution or buffer or whatever you have your sample in is higher than the pI of the protein, what would be your charge? Net charge. Sophia? Negative. That is true. Above the pI, the protein donates protons to the base because you have high pH, higher pH, you have more OH minuses, then your protein is donating protons. Then it becomes net negative charge. The opposite is true. If the pH is lower than the pI, you have acid in there, then the buffer will start giving protons to your carboxyl groups, and they will be protonated, and your amine groups are protonated. Therefore, you will have a positive charge. So if you know the pI, then you can determine at which pH you will have a negative charge or positive charge. Then you can decide if you want to use anion or cation based on what other proteins are in the system. Salting out, I'll just say that and then end here. Salting out in HIC, hydrophobic interaction chromatography. So you will inject your protein with under high concentration of salt. They will precipitate on the hydrophobic column because you will shield their charges, so they will interact via hydrophobic interactions with the column. The more the protein has hydrophobic components on the surface, the more they're going to interact. And then you start gradually decreasing the salt concentration, then you will gradually separate them off of the column. Okay, I'll stop here for next time.